Hi everyone, welcome back from Easter. Uh, Today I'm gonna just quickly wrap up the smart contracts talk, well, the blockchain talk that Rahul did. Um, so basically, there are a bunch of exploits you can do on smart contracts, but there's only really one that turns up in CTFs, and I'm going to spend most of this talk talking about it. I mean, it's not like it's a small vulnerability. It was used to steal, I think, 50 million quid back in 2016, I think, when a big smart contract known as the DAO, it got hacked by this vulnerability. After having an audit that confirmed, or at least claimed to confirm, that it didn't exist. So that was quite fun. And in fact, the hack was so big that the blockchain split into two, with one group of people sort of all agreeing, doing a sort of 51% attack, all agreeing that that hack didn't take place, so that the criminal didn't get away with the money, which was the bigger one, which is what currently is called Ethereum. And another one which was like, no, we can't do a 51% attack. That's against what blockchain's about, and kept going with the original chain where the hacker stole the money. That's called Ethereum Classic now. But anyway, that's enough of the history. Let's talk about how to hack. So this is a CTF challenge. I might accidentally leak the flag. So just by watching this video, you might get yourself a free flag. So this is the contract we want to hack. In fact, I got it coloured here, if I can do that. Yeah, brilliant. Okay, so Solidity, which is the language used for programming Ethereum smart contracts, is a bit like C, or a bit more like C++ or Java, and take your pick of which one of those you hate the most, where a contract represents a sort of class, and it's a class that can be called by anyone on the blockchain. So one important thing to note is that everything on the blockchain is public. So here I've marked, for instance, I don't know, if I created a variable which was, bool private secret data, anyone would be able to work out what the value of the secret data was on the blockchain, because the way smart contracts work is basically, as well as processing transactions, the nodes running the network and the miners running the network process small scripts. And to be able to process those scripts, they need to know what's in it. And since anyone can be a miner, anyone can read the data. So it's just an important thing to notice that nothing you put on the blockchain is secret. You can encrypt things, and then the plain text might be secret, but the actual ciphertext, the actual data you have put on the blockchain, is publicly viewable to anyone. So the only thing that private does as a modifier is, A, it makes your contract slightly cheaper to deploy, because public variables are more effort to manage, and therefore the price of deploying the contract reflects that. That also means that other smart contracts can't directly read those variables. It can only be done by someone manually off the chain. It can't be done automatically by something trying to interact with it. But anyway, let me get on to exactly what a smart contract does. So a smart contract in a blockchain setting is generally built to move money around under some rules. So if I open up a new one here, a.sol, you could, for instance, so I can make a classic one, which is, let's say you both, you have a bunch of people who want to pay money towards something, but only want to pay money when a certain threshold is hit. So sort of like a Kickstarter, but without continuous funding. So all the money comes in at once. So if I call it funding, you can define functions on this contract. So this contract is sort of an account. It's a bank account which can act autonomously. So, for instance, a function contribute, and it would be public and payable. You can get it to receive some money from a sender by the payable thing. If it doesn't have payable, then it can't receive money. It can only just be called like a function, rather than a function with extra money on top. And you can get, so I don't know, you could get to have a big table. A mapping is like a dict in Python of addresses to how much they've spent. So you can just say contribs, the contribution of the sender of the message, the person who paid the money, you want to add on how much they actually paid. An important thing to notice is that I haven't actually initialized this, but all objects in smart contracts are default initialized to 0. Leak equals ban. Yeah, okay. If I leak a flag, I get banned from the society. I think that means I won't be able to run in the committee. Right. Okay. So you can also have, once it's done, you could have a function which is when it's done. So we do require message dot address this. So casting something to an address, like I've just done there, means to treat it like a single bank account rather than treating it like treating it like a class. You treat it as like a user with its own balance and you can send money to, as opposed to a bunch of functions. It's a different way of looking at it. Sort of a bit like casting to a different type, casting to like a pointer, for instance, in C or something. So this is a require that the balance is greater than, let's say, 1 ether. And then we could say address, payable address 0 dot transfer address this dot balance. So what this will do is allow anyone to contribute money. I'll let me make this public. Allow anyone to contribute money. But once you've hit a certain threshold, anyone can call this fund function, which will check the balance is greater than 1 ether and transfer the money across. Now, what does this require function is particularly special. It's effectively the same as writing if and then revert. Now, revert is sort of one of the two most important parts from a security perspective of a smart contract. Revert is an exception thrown within the contract, but unlike normal exceptions in programs where you keep all the side effects you've done, so if you're printing to screen and then you throw an exception, you'll keep everything you've printed to the screen before. You can't undo that. In smart contracts are atomic. They either happen or they revert. Which means that if a revert function, if an exception gets thrown, every single effect you have performed gets undone. That means if you've deleted any contracts, you sent money, all of that gets reverted to how it was at the beginning of execution. And the reason for this is pretty simple. Writing code is difficult, especially in the presence of errors. Memory leaks are particularly bad, but imagine instead of leaking memory, you're leaking money. You want to make sure that you can't transfer money, undo a transfer in Ethereum or on a blockchain thing without, performing a 51% attack on the network. So this gives you a way of sort of realizing that you've made a mistake and undoing it within the context of a single invocation. You can't undo a previous call. So if I've sent money to someone and then the contract returned and then later on I tried to pull that money back, that can't be done. But within a sort of an instance, within a call of a function, you can undo all of its effects. So now we have a basic idea of how it works. I'm going to introduce the second function, and this function is probably responsible for more hacks than anything else on the whole blockchain. So it's called receive. If I can. External means it can't be called inside itself, and payable, it receives money. So this function is called whenever someone sends money to the contract but doesn't specify a function to send it to. So this is sort of, you can get it to act, this allows you to plug into things that would treat you like a person. So if you've got something that's supposed to send you, I don't know, you've got some bank that's, you want to withdraw money from, you can get it so whenever you withdraw money, it will call this function and handle it, and then invest it somewhere or something like that. You can get it to be automatic, and one of the most important things in computer science is to separate out components so they don't have to understand each other's internals to work. This allows you to a bank to not care whether it's talking to a user or a smart contract that wants to interact with its balance. It can just send it the money, and let the smart contract deal with it. But it does have a massive downside, which is many people don't realise that this is something that can be done. They think, oh, I'm just sending it to a person. They don't think, oh, but they can also execute code. There's no way of telling the difference, really, within Ethereum. I suppose there might be, but no one bothers to. So if I look at the DOA.sol, so this is the smart contract you need to hack for the CTF, and I'll explain how to do it. In fact, over here, I actually have the how to do it. Let me just hide that. So this is very similar to the sort of funding idea we looked earlier. You create it with some amount of money. You can put more money in, and you can take money out. It has some functions used within the code to check have you actually hacked it, and to disable it once it's been hacked. But you know, that's just to help the CTF run. It's not necessarily that important. So let's have a look. If you put money into it, goes to this dictionary, goes to your address in this dictionary, and adds however much you sent to the smart contract in this deposit function to the balance, to your balance, right? Then later on, it gets your balance. It checks that your balance is greater than equal to, it checks the amount you've requested is less than or equal to the balance in your account. You can't pull out more money than's in it. It then sends you this money by making you payable. So normal addresses can't have money transferred to it, so you have to explicitly say, this is an address I want to send money to, and sending you money with the value of how much you've requested. Then it deducts it from your account. Now, the way to hack this function is not immediately obvious. However, the problem is this balance is a global variable, effectively, which means that if this function somehow got called again within itself, any effects would affect both of them, both the inner call and the outer call. So, if I bring up the evil hack smart contract here, this is exactly what I've done. What it does is it deposits some amount of money into the contract and then asks for it back. But when it receives the money, when it's sent the money, when it receives it, it asks for the money back again. And because it's still executing this line, it hasn't gone around to deducting that from your account. So there's no this require balance greater than equal to amount. The balance hasn't changed, it's the same value. And so this can be called over and over and over again until you've drained all the money out of the account. Obviously, if you try and withdraw more money than's in the entire contract, then this thing here won't even call your function, it will error out. And remember, an error undoes everything, so you lose all the money. So that's not good. But if we stop ourselves when that happens, then we can just, we can terminate the recursive call, and then it will start going, the innermost one will get the old balance and take away the amount, and then the one above that will take the balance it saved and remove the amount, and we keep going until it's fine, until we get out to the top. Now, because all of these initial balances for every nested invocation of the function were the same, this value will be the same. And this is a classic example of atomic operation, why you need atomic operations, because we've done this in two parts. Someone jumped in the middle of it, and we're just saving the same number over and over again to this, which will be 0 because we're requesting all the money back out of the account. And so at the end, we'll have a balance of 0. We'll have sucked all the money out of the account, even more money than we originally put in. Now, you might be asking, isn't this a bit contrived? I've split this up into two parts, rather than just doing what you can see here, plus equals, why haven't I done minus equals? Well, the reason for that is because I was writing this code yesterday, and then I realised that they had actually done something pretty clever. So, in the old versions of Solidity, this language, there was what's known as unchecked underflow and unchecked overflow, similar to C and C++, where if you write, for an unsigned integer, if you write 0 minus 1, you end up with the maximum possible value. Because it tries to go to the number below 0, it fails, and because of two's complement arithmetic, or because, if you want to look at it this way, because it forms a cyclic group, however you want to look at it, it goes back, it wraps under and goes all the way back over to the maximum value. Because minus 1, if you look at it as it's represented on a computer, is actually written as, in hexadecimal, 0x f f f f f f f f f f f f f f, as many f's as it can get in there. And the reasons that are a bit complicated, and I'll not get into it, but basically, an underflow of an unsigned integer causes it to go to the maximum value. And actually, with a signed integer, if you have 0x f f f f f f f f, which is minus 1, and you add 1 to it, you get to 0. So if you if you go to the maximum possible value, which I think is 0x8 f f f f f, and add 1, you actually end up going to the negative of the largest value, I think. It sort of wraps round in a loop. If you keep adding 1 to an integer, it will go through all of its values, including any negative values. But anyway, why is this important? Well, because if we did this as one operation, let me comment this out. So we write this as minus equals, then each time we call the loop, we'd be taking away amount. We should get it to be negative at some point. And because this is an unsigned integer, this would wrap round to the largest possible value, which would mean that just by executing this a couple of times, instead of having to write complex code, we just withdraw our balance twice. Then what happens is our balance shoots up to the maximum possible value, or close to it. In which case, since this is a 256-bit integer, that's about 2 to the 256, which I think is approaching the number of atoms in our universe sort of scale. And so you can then just withdraw money as you would normally. You've now got an insanely high balance. Obviously, if you try and withdraw more than there is in the smart contract, it will crash and revert. But if you are sensible with it, you basically have infinite balance on this bank. And it wouldn't necessarily be obvious that you've done it to anyone who wasn't rigorously checking that because everyone else's balance would appear to be the same. It's just the money in the smart contract would be going down. Someone would have to manually audit it. So, if I have a look at this, let me put this back to how it was, and I'll quickly. Oh, and there was others, and I'll demonstrate the other vulnerability, which is quite common. I think it's. Where have I put it? Here. Right. So, this is an auction contract, if it'd like to load. Yeah, this is an auction contract. This is actually written by one of the Cybersock members. This wasn't written for the CTF, because this is actually, I only found about this yesterday, actually. It's quite a subtle vulnerability. So it's very simple. What happens is, you give it some number of tokens, like NFTs or whatever, and you pay money to bid against other people for this thing. In this case, it's Glizzy Coin. It can be anything you particularly want. And the way it does it is here. So first of all, it checks, has the auction actually started? Have you bid more than the minimum bid? And have you bid more than anyone else? It then updates the money, transfers the amount to the last bidder, and then emit bid, that's an event that basically writes on the blockchain, someone bid something. It doesn't actually have any effect other than making writing code a lot easier for the blockchain, but only for externally interacting with it. You can't see events inside it. It just basically attaches a note to the block saying this event happened. Now, if you notice, the person who wrote this has been very clever in avoiding re-entrancy vulnerabilities. They've set the value and then transferred the money, which means you can't have a re-entrancy vulnerability. Or if they re-entered it, all which would happen is they'd have the previous state. They'd only be able to bid as it were before. This is just at the return of the function, ignoring the emit here, which doesn't have any effect on the state. this transfer here is well placed. Now, there is, however, a significant vulnerability with it. So I think I have it deployed here. Let me just close down the auction and do this. So I have two contracts here. I have a normal bidder who can receive money, can bid and claim. You can make the actual contract a bit more complex than this. There's actually no way of taking the money and the Glizzy coin out of the contract, but you know, it's a simulation of one. This is done on a sort of simulated blockchain, not a real one. So don't worry, anyone who's holding Glizzy coin, we're not burning any here. This contract is exactly the same. It imports it. It's like inheritance in Python or Java or whatever. But we've replaced the receive function with just the word revert. So remember, revert undoes everything. So if we bring up the auction, if I can compile this, there we go. I'll deploy an auction here. So it wants the address of the token. It wants how many blocks we bid for, and it wants a minimum amount we bid, which I'll put as 1. So if I create that, and then send it some amount of tokens for it to be bid on. So transfer that 10. Cool. And then start it. You'll see that it's got 10 Glizzy coin for sale. No one's bid on it yet. You can't claim it. You can bid on it, and there's 9 blocks left. So let's deploy our normal bidder, if I can bring up that. So our normal bidder, who honestly just wants to get some Glizzy coin. So we put the address in there. We want to transfer it 1, so you hit the minimum bid. And there we go. The highest bid is now 1, and if the bid keeps going, if no one else bids on it, we get the Glizzy coin. That's nice. If we try to bid 1 again, if we try and bid 1 again, it fails. If anyone else tried to bid 1 again, it would fail, because someone's already bid 1, you have to bid higher than that. So, demonstrate, I can put 2 there. There we go. So we now have the highest bid being 2. Let's put our evil bidder in. And this is quite an interesting vulnerability. This isn't one you would necessarily expect. I'm going to outbid the previous contract, the normal bidder, with 3. So I click the bid button. There we go. If we try and outbid ourselves again, you'll notice it fails. Because if we look at the bid function, it tries to transfer the amount to the evil bidder. But when the evil bidder receives the money, it just says, wait, no, there's something wrong, and crashes, which undoes the whole thing. Which means if anyone tries to bid, the bid function itself reverts and undoes their bid. So there's no way of bidding higher. So let's see, how many blocks do we have left? We have 2 blocks left. Even the evil bidder cannot outbid itself. If I try to put it at like 1,000, right, and try to bid, it would fail because it would try and send the money back to the bidder. And in fact, if I have, let's just do that again, 1 more block. So 0 blocks, so it can now claim it. Oh, actually, before I claim it, let me just show you that it's got no balance. So the balance of the evil bidder is 10. Have I copied that wrong? Yes, I have. Sorry. The balance of the evil bidder is 0. But once we claim it, the balance goes up to 10. So it's taken the Glizzy coin from the contract because it won the bid, and because no one else can bid on it without crashing the contract. Does it? Also, I've seen a message. Does it revert if it underflows? Yes. Sorry, that's in modern versions. So in anything Solidity version 0.8.0, which is quite recent and above, any underflow or overflow. Overflow is much harder to trigger with Solidity because it defaults to 256-bit integers. But any overflow or underflow counts. It gets an exception. It reverts exactly. There is a library for previous versions called SafeMath, written by the Open Zeppelin group, who are amazing. They write like really good code that you could just copy and paste. You don't need to worry about these vulnerabilities. Okay, don't copy and paste random code from the internet, but they're used by a large number of quite big smart contracts. The they have a safe math library which emulates this behavior, so you can do addition, subtraction, whatever with it. And if it throws in, if it overflows or underflows, it throws an exception. So yes, you can get it to revert on previous versions, but on 0.8.0 and above, it does it by default. There is currently a bit of a pressure group to undo that behavior, because I suppose this is an important thing about smart contracts, is that everything you do on a smart contract costs money. It's not like with CPUs where it makes it take slightly longer, or it might be running in the background or something. Every single instruction you run on the EVM blockchain, so on the EVM, the Ethereum blockchain's sort of emulated processor, every single instruction you run costs money. Transfer and similar and function calls cost a lot. I think it's 21,000 gas, whereas individual things like small operations can cost like about 3 or something like that. And the idea is to stop someone just like writing a smart contract that loops forever, which makes transactions impossible to mine. In fact, on one of the test nets called Ropsten, someone found a way around that. Basically, they found an inaccurately priced opcode, an instruction that was way too cheap for the effort it took to compute, and just spam transactions containing that, and no one could run a node on the blockchain because it just took so long to run through all that stuff. So yeah, and there's a limit to the amount of gas you can have, and in fact, sending money to someone is on Ethereum, there aren't transaction fees; they're gas costs. You just pay the flat fee of 21,000 gas for the transaction, as if you were a smart contract. And so instead of having a sort of block size limit, it's got a block gas limit, which is how much stuff can happen within a single block. And that's why Ethereum transaction fees are currently really high, is because you are not just bidding against other people trying to send money to get into the block, but you're also bidding against really complex smart contracts, which use up most of the gas, who are trying to automatically trade things. But that's the whole thing. That's probably more Rahul's side than mine. But yeah, so that's how you can cheese an auction. And so the way you patch this, of course, is by using send, which if I compile, there you go, which returns false if this ever's out, rather than reverting the whole thing. Let's see. Yeah. You could also actually, I think, yeah, that's basically the only way of doing it, is not reverting when something goes wrong, unless you have to, unless you depend on its effect. Don't revert if you can't send the money. If they're not able to receive the money, if they aren't able to refund the money, then you can't really do anything else. You can't find any other way of giving it to them. So don't bother reverting. For the reentrancy vulnerability, you need to make sure to reentrancy vulnerability, you need to make sure to do your effects before you call an external contract. And this reentrancy vulnerabilities aren't always this simple. There are instances of it spreading through their multiple functions, sort of a bit like race conditions, where each individual function can be fine, but working together they cause big hack. So you basically sort of need to do a more holistic analysis of your thing. You can do things like locks, so if a function's being called, don't allow it to be called within itself. Or if you have a bunch of functions acting on a single piece of state, don't allow any of them being called if one of the other ones is being called. Sort of, you can bring a lot of what you know from synchronization of threads across into smart contracts, even though it's a single-threaded thing. Which is fair enough. Right, so let's see, what else do we got? Oh yes, and for overflows, just use the safe math library. Like, if you're unsure about whether you have the right version of something, just import the safe math library. But yeah, that's pretty much it. If you want, I have set up the CTF. You can it's now really easy to set up. I can walk people through that if you want. It's just, you just connect onto install an extension to your browser, You copy and paste that stuff, and then you just connect it. You can get free money by clicking this link to test things with, and you can have a go at the CTF challenge here. So yeah, I'll be in Discord, and I think I will see you all there.